Here in this video, we're going to look at reviewing our inverse trig functions and right triangles. The first example we have here says we want to evaluate the expression without using a calculator. Of course, you could enter this in the calculator, but we want to look at how can we simplify this, the cosine arcsine of 5/13. Well, the first step into solving this is you want to look at where's your right triangle. In other words, here we want to use the arc sine of 5/13. Okay, so we want to look at this part here. So if we think of this, the arc sine of 5/13, that's going to give us an angle theta. So we want to determine where is our angle going to be located. Well, the arc sine we know is y over r, and we know that the 5 is positive, so that means we're going to go up 5. So that means our triangle, in other words, our angle theta, must be in either the first or second quadrant. Well, because our arc sine, if you need to review this, go back and review your domain and range for your arc sine, your inverse trig functions, says that the arc sine is only going to be worked from negative pi over 2 to a positive pi over 2. So that's looking at the first and fourth quadrant. So therefore, our triangle must be in the first quadrant. So in other words, here we have our angle theta. Our y value is 5, so we're going up 5. And then the hypotenuse is 13. And then, of course, we can use the Pythagorean Theorem to find the missing side. So this is going to be the square root of 13 squared minus 5 squared. So that would be the square root of 169 minus 25. And then that's going to be equal to 12. So now, once again, all we did was use the arc sine of 5/13 to draw and label our triangle. Now we simply want to find the cosine. Well, the cosine of this angle theta, so if we're looking here essentially for the cosine of theta, then we know the cosine is x over r. So therefore we're going to end up with 12 over 13. Okay? So again, this is just kind of a review of how to deal with your composite functions involving your inverse trig functions. All right, here we have another example, and again, you may want to pause the video to see if you can come up with the answer for this one. We have the secant of the arctangent of a negative 3/5. So the first thing we want to look at is where do we draw our triangle? Well, because we're talking about the arctangent, we know that that's going to be y over x, and we know that we could take the negative with the 3 or the 5 because your y or x could be negative, and the question is, are we going to have a negative y or a negative x? Well, if we think about again the domain and range of your arctangent, once again we know the arctangent is only defined from negative pi over 2 to a positive pi over 2. So that means our right triangle must be either in the first or fourth quadrant. Well, if x is negative, that's going to have to put us in either the second or third. So therefore, our y must be negative. So that means we're going to draw the triangle in the fourth quadrant. So if our y is negative, then we would have a negative 3, and your x is a positive 5. And then once again, we need to find the hypotenuse, and we could use the Pythagorean theorem. So we know that's going to be the square root of 5 squared, which is 25, plus negative 3 squared, which is 9. And then we would end up with the square root of 34. So again, that allows us to locate our triangle, label the triangle. Now we're simply looking for the secant. Well, we know the secant is going to be equal to r over x. Remember, the secant is the reciprocal of your cosine function. So the secant then would simply be the square root of 34 over 5. Okay, so now we want to look at another example, but you notice here this one is in terms of 4x. We don't have just strictly numbers here. So it says write the expression in algebraic form. We have the secant of the arctangent of 4x. Well, once again, we need to label our right triangle. Now, usually they're going to have to specify the value of x or the angle here for x. So we can't really determine because we don't know what the value of x is. So we can't determine exactly where the right triangle is going to be. Most of the time when you read the directions, they're going to tell you that you have an acute angle, which simply means that your angle is going to be in the first quadrant. So therefore, when we're looking for theta, our right triangle is going to be drawn in the first quadrant. Now, if they specify otherwise for the value of 4x, maybe they tell you that it's going to be located from pi over 2 to pi or some other quadrant, then that's where you're going to draw your right triangle. A lot of times when they give you this 4x here, a lot of times that's going to be in the first quadrant. Well, once again, we have the arctangent, so we know that we're talking about, in this case, tangent is y over x, okay? So that means that we would have our y value would be the 4x, and this is understood to be over 1, so therefore this would be our x value is 1. And if we want to find the hypotenuse, then that's going to be the square root of 4x squared, so that would be 16x squared plus 1 squared, which is 1. Now we've labeled our triangle, so now all we have to do is find the secant. Okay, so we're looking for the secant, and the secant, once again, is going to be, in this case, the reciprocal of our cosine, so we're looking for r over x. So in this case, we would end up with the square root of 16x squared plus 1 over 1, so that's our answer. Now, you're going to find this useful the further we go along here with looking at some of our integration a little bit later on, or taking derivatives. So make sure you understand here how to draw and label your right triangle. All right, here we have another example, the secant arcsine of x minus 1. All right, once again, we're going to assume that we're looking at an acute angle, so we're going to draw our triangle in the first quadrant. And because we're talking about our arcsine here, we know that the arcsine, the inverse sign here, our sine function deals with y over r. So our y value is x minus 1, and the r value is 1, because this is understood to be over 1. And once again, we can use the Pythagorean Theorem. So that's going to be this a squared plus b squared equals the hypotenuse squared. So that means we're going to take the square root of 1 squared minus x minus 1 squared. And if we do that, we'll have 1 minus x squared plus 2x plus 1. And if we distribute here now, we would have 1 minus x squared minus 2x minus 1. And we can simplify this a little bit. 1 minus 1, the 1's cancel out. So you're left with a negative x squared minus 2x. So now that we have our triangle, we can come over and find the secant. And once again, the secant is, we're looking for the secant here, the reciprocal of your cosine, which is r over x. So the secant here of our angle is going to be equal to 1 over the square root of a negative x squared minus 2x. All right, here we have one last example, and this one's just going to look at simply solving the equation for x. We have the arctangent of 2x minus 5 is equal to negative 1. So how do we solve this? Well, the first step is we need to take the tangent of both sides of the equation. So therefore, we would end up with the tangent of the arctangent of 2x minus 5 equals the tangent of negative 1. Well, of course, the tangent and arctangent is going to cancel out, so we're left with 2x minus 5 equals the tangent of a negative 1. And then we need to get rid of the 5, so we would have 2x is equal to tangent negative 1 plus 5. And then we can divide by 2, so x is equal to the tangent of negative 1 plus 5 divided by 2. And that's our answer. And of course, you could put this into the calculator and you could come up with an approximation. The tangent of negative 1 plus 5. Now again, make sure that you put this in parentheses before you divide by the 2, and you should end up with approximately 1.721. Okay, so there's kind of a review of your inverse trig functions, how we can handle composite functions, and a quick review of how to solve an equation involving your inverse trig functions.